Greetings and welcome back to another discussion on my channel. Today we are very pleased to bring you a topic that I do not think I've ever addressed on this channel before, at least as directly or in as much detail as we're going into today. The topic today is physics and the notion of naive physics, which is basically what human beings intuitively think when it comes to concepts such as energy, heat, motion, etc., and how they interpret the world, and how this oftentimes contradicts the actuality of our physical realm and our physical situation. Now, as I am somewhat informed on physics, but it's probably my weakest science, I will not be doing most of the speaking today. No, instead we have effectively our resident expert on all matters physics, Francis. Some of you might recognize him from the cafe, others you might not know him at all, but he is very knowledgeable on the subject, and we are going to slog through all the issues that arise when we try to understand the world as it is, as opposed to how we intuitively think it is. So with that said, I will introduce Francis. Thank you for joining me, and let's get started on this.
Thanks for having me on. It's going to be really interesting. So like we discussed beforehand, I think that a good place to start would definitely be just energy, and some of the misconceptions about that. For instance, we've got kinetic energy, which is energy due to motion, and this is as simple as a basketball being thrown through the air that has kinetic energy. And what that means is that due to its motion, it has it's got innate energy to it. So this energy, as that basketball strikes the wall, for instance, that kinetic energy that is lost into the wall, because as you know, the ball is going to hit the wall and then bounce away. As that ball hits the wall, some portion of that energy is going to push particles away from the ball as it moves back towards you or as it falls to the ground, and some of it is going to cause vibrations in the wall, which is going to lead to, for instance, the wall is actually going to heat up because of that. Like the particles in the wall are going to start to vibrate. You don't have any sort of energy loss in the universe, so it's not created nor destroyed. This is a law that dates back to, I want to say, the 1880s, with a French scientist whose name escapes me right now. Yes, a good definition of energy would be, in physics, energy is the property that must be transferred to an object in order to perform work on or to heat the object. Energy is a conserved quantity. The law of conservation of energy states that energy can be converted in form, but not created or destroyed. So that gives us a pretty good launching point.
Just briefly, it's interesting that in defining energy, there was a discussion recently where a gentleman tried to, because he didn't understand what energy was, tried to use this idea that after death, some part of you lives on in the form of energy, not understanding that energy is a property that interacts with the matter in your body, and that's just a physical impossibility. You don't have this thing floating in the ether. And I think that's why it's really important to sort of define this, because a lot of people, and we have a kind of a layman's understanding in society of what energy is. I mean, we have this, I have no energy and I'm tired, but also this idea that energy is something independent of your physical body, which is ridiculous.
Oh yeah, certainly. A good way I like to think about it is you can have our body's sort of like a wind turbine, in that it requires that input for the like the moving parts to to start to go, which would be in the case of a wind turbine, would be like the air particles striking the blades, which causes it to spin, which causes generation of electricity. But with humans, we have all these little bits and moving parts inside of us that require that input of energy. It's certainly not any sort of spiritual thing.
Yeah. Okay, so we've covered the basics of energy. I believe we're going to then move on to, go into some of the history in terms of heliocentrism versus geocentrism. So maybe we should start there.
Oh, okay, yeah. So, initially, humans, if they even thought about this at all, were under the conception that when they looked out into space, this thing that they would see, this universe, as we came to call it, or this solar system in some, if they were able to notice the planets, was considered that it was never considered for at least a long time that Earth would be round, that the Earth may not be the center of the solar system, that we may not be as important as we think we are. So I think it was around the 3rd century BC. Aristarchus of Samos was actually one of the first to propose that the sun is at the center of the solar system, and it wasn't given really any thought or much. Nobody really looked into it, but it really during the I don't remember the exact time, but essentially Copernicus came along.
That's Copernicus' 15th century.
Yeah, thank you. Yeah, so during the 15th century, you have Copernicus coming around and making the claim that the Earth is not at the center, and in fact, the Earth has a daily rotation and a yearly orbit around the sun. So, at the time, that totally goes against everything that people would sort of perceive.
Should probably mention that the geocentric view that everything in the solar system revolves around the sun. This was developed allegedly by, or at least its primary exponent was Ptolemy, and this was inherited by the church, which is why it became a type of orthodoxy that was, you could say, bound up with the church, and any discussion that might have contradicted that, and of course was, as I said, late 15th century and 16th century, would get you in a lot of hot water, because the church wasn't really about explaining planetary movement in the most accurate way. They were about their own authoritarianism. Oh, certainly.
Actually, so a lot of the problems when it comes to the church having negative views of the heliocentric model comes from a certain scientist. I want to say his name was Tycho or Bronze. He was like a clergyman at one point, who turned heretic. He started looking into he converted over to the Protestant church, stating negative things about the Catholic Church, but he also held the heliocentric model above the geocentric model, and so it's sort of by proxy, by virtue of him having both ideas, both ideas ended up in that state of being considered heretical. He was then burned at the stake, mostly because of his own hubris, he actually passed through a Catholic city on his way across the continent, hiding from the church, and was arrested basically in the Catholic capital of a region, rather than just traveling through Protestant areas. He ended up, just because of his own hubris, getting caught. So I think it was around the 1830s that the Catholic Church actually formally sort of de-hereticized the view of heliocentrism, which, to anyone who doesn't know how, for instance, one way we know that the Earth is a sphere and not flat is during those eclipses where the Earth is between the Sun and the Moon, and you see the Earth's shadow cast on the Moon, you'll always see it as a very distinct curve, rather than if it was flat. If it was a disk, for instance, you'd see very different shapes. You'd see, for instance, like a line across the Moon, or you'd see just a long curve rather than the spherical curve that we very clearly see on the Moon. So when we're to those of you in the audience who don't know why the Earth is sphere, and one way that we know this, for instance, rather than whatever the flat earthers think it is, maybe it's like, to them it's just a square plate, maybe it's an endless stretch of land, maybe it's I honestly don't know what they think. I do know they think that the Earth is not round, but is in fact just a flat plane, which is of course absurd. One way that we know this is during the eclipses, where the Earth is between the Sun and the Moon. Instead of seeing just like a straight line across the Moon, or some variation of that, we see in fact a very distinct curve in the shadow, which would only be the case from all the different angles that we receive these eclipses under. That we would only see that if the Earth in fact was a sphere. So it's just a very simple way that you can make an observation in real life that the Earth is in fact an oblate spheroid.
The perception, it makes sense that human beings, when they first look at a landscape or just look at the world, the Earth, they would think it's flat. It doesn't, quote unquote, look round. If you just use your simple human ape vision, it just looks like a flat landscape. It makes sense that people, at least in the beginning, would just assume that's the case. What doesn't make sense these days, I don't want to go too much in this, is this notion that the spheroid nature of the Earth is it's just a lie. But let's not go down that rabbit hole. But it certainly makes sense from an intuitive perspective. It's just people using what their senses give them. It looks like it's flat, so it probably is flat. Mm-hmm. And people, and related to this topic, they're all, you look at the Aztecs, who would ritually sacrifice people because they worried that the sun might not rise, not understanding the slightest of anything about rotation. They just thought that everything was predicated on whether or not you appease the sun god. And there are all kinds of silly notions and dangerous notions that arise from a misunderstanding of our physical reality. That's just one of them. But so that is something that I think most people know, or at least it's very sort of basic when we talk about most people, even if they know nothing about physics, know that the world is a sphere. Mm-hmm. The Earth is a sphere. Even if they don't know particularly why or the details, they kind of know that. But the final point on this would just be that obviously it doesn't look that way if you just look out your window. It doesn't look like we're on a sphere. But then we get into things such as gravitational fields, which obviously gravity. I think the layman's perception or the human perception of gravity is, it's this thing that makes stuff fall down, and that's about as ooga booga as you could describe it.
Yeah.
So when we actually talk about gravity and gravitational fields, apart from the ooga booga explanation, how would we describe that?
Okay, so gravitation is obviously pretty complex, but there's a very simple way of describing it. So imagine you're a child again, and you've got in your backyard a trampoline. Now, you can go sit in the center of this trampoline, which causes a depression in the center, and then anything dropped on the outside, like for instance, if you were to take a ball and roll, and let's say that the trampoline is also frictionless, right? So the ball can roll without slowing down due to the interactions between the sort of little canyons in the matter, the little the deformations in the matter, but because nothing is actually perfectly smooth, but we're going to say that in a vacuum this trampoline is perfectly smooth. So if you were to sit in the middle, and then around you someone rolled a ball onto the trampoline, and it would roll inside of that depression on the walls of the sort of like conic shape that you're creating on the trampoline. And that's very similar to gravity, but gravity of course works in a three-dimensional way. So essentially we've got this, and this is Einstein's way of describing it the way that I'm doing this, is that you've got a sort of rubber sheet where things cause depressions, but in the three-dimensional way, and then things will ride those depressions. They'll sort of circle about them, riding on these curves in space. So it's not really a quote-unquote real force in a way. It's more of a displacement of what's a good way of putting that? So I'll just read the definition that I got offline for to be perfectly clear here. In physics, a gravitational field is a model used to explain the influence that a massive body extends into the space around itself, producing a force on another massive body. Thus, a gravitational field is used to explain gravitational phenomena, and is measured in that doesn't matter. In its original concept, gravity was a force between point masses. Following Isaac Newton, Pierre Simon Laplace attempted to model gravity as some kind of radiation field or fluid, and since the 19th century, explanations for gravity have usually been taught in terms of a field model rather than point attraction. So in a field model, rather than two particles attracting each other, the particles distort space-time via their mass, and this distortion is what is perceived and measured as a force. In such a model, one states that matter moves in certain ways in response to the curvature of space-time, and that there is either no gravitational force or that gravity is a fictitious force. So, yeah, it's not real. Like, there's not like the Futurama actually gave sort of a misconception, which we don't know if this is the case, I suppose, of gravitons, because I remember in several episodes Professor Farnsworth would say things like gravitons and graviolis causing like as a sort of gravity radiation that things would displace, that would, like, I suppose, push in on the planet, but that's not the case. It's simply deformations causing curvature in space-time, which things can ride along the curvature of.
One of the issues with gravity, I think, from the intuitive perspective, is you could say the limitation human beings have dwelling on the Earth, because all we have, I mean, historically, prehistorically, is our environment and the relationships of objects in our environment to gravitational fields in the Earth. We had no conception of how things might operate in a vacuum, because I don't. That's actually an interesting question. I don't know the answer to. When did human beings become aware of the vacuum, for example, as opposed to Earth?
So early explanations of the quote-unquote vacuum, and it's I don't recall exactly which scientist initially thought this, but he considered that which lies outside of Earth, outside of the Terra, would be a sort of ether, which he thought was actually like a form of like clear matter that the planets moved through, which, as we know, is not really the case, but not necessarily not the case in a certain way, because the vacuum is actually, sort of full of energy. It's full of electromagnetic radiation, little bits of matter, and even larger bits of matter, of course. It sort of escapes me as to what the when the initial
wow, that's not terribly relevant. Suffice to say that one of the issues with relation to gravity and I guess motion in general is that, I mean, it's the famous, right, you drop a bowling ball and a feather and blah, and everyone thinks the bowling ball is that thing, on Earth at least, the appearance of something not being the way it actually is, and that kind of leads up to friction, I guess, is an important concept related to this.
Actually, interestingly enough, I googled it while we were during this. It turns out that when it was first proposed, based on this, is 335 to 269 BCE.
Oh wow!
Yeah, so this was under Strato of Lampascus. He rejected the idea of a force pushing light objects, such as air, upwards to counter the force that pulls heavy objects down. He argues for the existence of a vacuum and showed that because air can be compressed, voids must exist between the particles of which it is made up. And it's a very for his time, that's quite an observation.
It's insane, with no tools to have to detect this. Wow.
Yeah, that is really quite something.
So when we're again talking about gravity, how does friction relate to all of this, and what is friction?
Okay, so friction, and this is a misconception a lot of people have, I'm certain. So friction is actually a product of electromagnetic fields or rather electron fields. Basically, the repulsion between electrons, between atoms. So, for instance, we'll start by I'll have everyone put their hand on their desk and push down. So when you push down, you're clearly applying a force to your desk. But as you can feel, as you push down more and more and harder, you feel that there's something pushing back against your hand. You can feel that not simply are you pushing down, but there's something normalizing that force. Otherwise, wouldn't you just pass through it? Well, yes, that's because of the repulsion between these electron fields. And I won't get too deep into why that is. But essentially, now, if you try to drag your hand to the left while you're pushing down, or to the right while pushing down, you feel that there is something which is holding you back. And what it is that desk that looks smooth to you, that may feel sort of smooth to you, is actually just full of these little dips and these large peaks of matter. And what happens when your hand is pushing down on this? Some of those peaks and some of those valleys in the matter, and I'm calling them that because if you're looking at them on the subatomic scale, they would very closely resemble that. Basically, these peaks on the matter in your hand will line up with the valleys sometimes in the matter, and when you pull across it, you're basically fighting that force. You're pulling past it, and the matter in your hand will bend. Those big peaks will sort of bend out of the way and then snap back into position, and then bend out of the way and then snap back into position. And which actually that's exactly why you have heat created from that friction, because as you'll feel as you slide your hand across, it sort of feels warm, and that's just vibrations of the matter, which that's all thermal energy is. It's just this bit of matter is vibrating in place, which I suppose that's there's actually a fun way of looking at it. If you touch a hot stove, what your brain then tells you as it fires those nerves that say, don't touch that, that's hot, ow. It tells you move your hand, and it gives you incentive to do so, because nobody likes pain. Well, that's not true, but some people I suppose do. But this particular type, heat, what your brain is telling you is, hey, the matter in your hand is vibrating to the point at which it's destroying itself. It may be becoming a gas that it gets so much energy that it's able to that it just bounces off of your hand and flies off and just floats off into the air. But yeah, friction is totally a product, as are many things, of the repulsion between electrons, which is definitely not intuitive at all.
We have no way, without tools, of unless you just speculate, get lucky, or really insightful, of even knowing that electrons are present. We can't see them. We can't even see molecules. So, with our eyes at least, things just look like objects to us, and that's it. So, I think this is, again, something that probably could not have, apart from some of these unique thinkers back in the day in ancient Greece who were really insightful, just could not have been known up until recently.
Yeah, quite so. Actually, a really interesting experiment that, I want to say it happened in the 1790s. No, it is 1790s to 1850s, somewhere around there. This gentleman had a atomizer, which is essentially just a very fine sprayer device, and it will separate liquids into a sort of into a very, very fine mist. And what he would do is he'd have two charged plates in a container, and he would spray oil droplets in there, and then I think it was he would project ionizing radiation into the container, and these oil droplets would then be suspended between these two charged plates, and then via a microscope which he had attached to this device, he would view inside, and he measured the dimensions of the oil droplets that were being suspended, and then was able to fairly accurately describe both the size and the amount of charge in an electron. So that was an incredibly intuitive experiment. It's incredible that man came up with something like that.
Yeah, I mean, the earliest interpretations of matter were really idea that spirits animated things, rocks, waterfalls, whatever, and they somehow governed the world, and that's why you would revere them and worship them. And later, these things became anthropomorphic in the form of deities and gods, and we certainly have come a long way. Now, when we come to talking about friction, there are different types of friction, obviously. There's fluid friction, lubricated friction, skin friction, internal friction, etc. Let me just briefly cover the different types of friction before moving on to the next component.
Okay, so dry friction, which isn't actually the, or we're just going to start with that one. Dry friction, which isn't actually the name that is used whenever we're like problem solving in physics. It's actually called static friction between non-moving surfaces, and then you could also describe dry friction as kinetic friction. And this would be something like you've got a wooden block sitting on a wooden ramp, and as it's sitting there, and we'll say this ramp is slanted, right? And as it's sitting there, you notice it doesn't slide down. And of course, as we discussed, this is because the interactions between the peaks and the valleys within the matter, being held in place by electromagnetic forces. So what static friction is it's the amount of force required to actually start to budge that block down the ramp. So if you were to grab the block and start to pull it down the ramp, it would require X amount of force to move it down the ramp, and then you would notice as you start to move it, it gets much easier to move, and that's what we call kinetic friction, and that's friction between moving surfaces. And the reason that you have this difference in levels of force or magnitudes of force required to move this is because the peaks don't have time to fall down into the valleys of matter, so you end up sort of skidding across the top of it, and that's what causes that vibration that you feel. It's just the macro of all those little micro skidding effects that you feel across the surface of the block and of the wooden ramp is going to cause it to vibrate, which of course is going to cause heat to form. And then we can look at fluid friction, which describes the friction between layers of a viscous fluid that are moving relative to each other. And so you could have, for instance, oil, traveling across the surface of, we'll say, water. And what you're going to see is that there's actually going to be a sort of static layer in between that's going to sort of stand still as the oil over the top flows and the water underneath flows. At least I think. I'm not an expert of fluid dynamics, but anyway. And then lubricated friction. So you've got, for instance, a gear that is turning with actually a gear is not a good let's say you've got a metal pole sliding inside of a metal tube, but you've gone ahead and poured oil down inside of it. So what this oil is going to do is it's going to create a layer between the rod that you're inserting into or the pole that you're inserting into the tube, and essentially it's going to create a layer in between where one side, the side that is sticking to the pole you're inserting, is going to be moving down with the pole, and then there's going to be and then there's going to be a layer that's stuck to the inside of the tube, and there's going to be a layer in between in which these two pieces of matter are separated, and the friction is reduced, so you're able to actually slide two things past each other using liquid as a or gas for that matter, because gas is sort of a liquid, and you're going to be able to slide them past each other because you don't have the problem of these very rigid peaks and crests, or peaks and troughs, or peaks and valleys interacting with each other, because they're going to be separated by a layer of liquid. And then skin friction is a component of drag, the force resisting the motion of a fluid across the surface of a body. And again, I'm not an expert of fluid dynamics, but this would be something like pouring, let's say, honey across like down a wooden ramp, and this would be due to you would see the honey would fill those crests and troughs, or those crests or those peaks and valleys, and then it would resist the movement as it passes down that, which I suppose you would see honey poured down the surface of glass would actually run quicker down the glass than it would down a wood block at the same angle, and I suppose that's because glass is more smooth than a piece of wood. And then you've got internal friction, which is the force resisting motion between the elements making up a solid material while it undergoes deformation. And that one's really interesting. So you've got, for instance, a large like a block of rubber, and you're taking a press, like an industrial press, and you're pushing down on it. And what you'll see is that these different types of matter, or the rubber is going to hold on. I'd have to think about this one a little bit, to be honest, because I haven't looked too much into internal friction recently. But yeah, those are the different types of friction.
Relating to all of this, I mean, one of the basic questions is why do humans typically, when you ask them if you drop a bowling ball, does it drop straight down or move forward? In the context of all of the things we've been discussing, why do human beings say incorrectly it just drops straight down?
Oh, well, of course, that would be because we are. That'd be, of course, because we're on Earth, and just intuitively, we know that things go down, which is actually just towards the center of the Earth. Is that what you're talking about?
Well, yes. Basically, that a bowling ball would, in a vacuum, behave differently.
Mm-hmm. Oh yeah. So if you've got a bowling ball and you're in a vacuum, right? You're on the moon. There's no air on the surface of the moon in this instance. I'm sure there's a little bit, but in this instance, you're just standing on the moon. There's no air. There's no atmosphere at all. So you've got a bowling ball in one hand, and in the other hand, you've got a pillow. And when you drop these, you're going to notice that they actually fall at the same rate. And this is because, as we discussed earlier, the gravity is just the result of things sort of riding along the curvature in in the gravity field that the moon is creating. So the moon is going to put out X amount of force on every object that it interacts with. It's not going to put more force on the bowling ball or less force on the pillow. It's going to put out the same amount of force. What will be different is that the bowling ball will put out more force on the moon than the pillow will put out on the moon. So the moon will actually, if you drop this bowling ball from about 5 feet away, the moon will actually sort of ride along the curvature of the bowling ball is creating, not to any degree that is perceivable, but it will technically. And so when you drop this bowling ball and this pillow at the same time, you've got like a hook that connects both of them to like some wires, and you can release them both at the same time. They will fall and they will both strike the moon at the same time. And this is because, and you wouldn't see this on Earth, because the drag created by the air resistance would, as we know, slow the pillow down, and the bowling ball would hit, and then the pillow would hit.
Yeah. And again, we prehistorically had no relationship to vacuums or no knowledge of that. So that would explain a lot of our intuitions here. And it's interesting that Wojak made a video a little while back. Even well-trained physicists, if they're tired or just not focused, can resort back to quote-unquote intuitive physics, as opposed to the things that they've learned and studied even for years, many years in some cases.
Yeah, it's that is a problem, although not a very serious one. Sometimes, as you said, when you're tired, rather than thinking, I need to do this for this to happen, you're working on a project, you'll just sort of fall into the instinctual level of I'm just going to do this regardless of the things that like if you're thinking totally logically about it, and you're being a physicist and trying to solve the problem, you're not going to you would know what you need to do, but that's not always the case, especially when you're tired, as Wojak has pointed out. That is something that I encounter in my daily life, which I'll just point out. I work as a mechanic, and I'll often make mistakes without thinking. Like, afterwards I'll look back and I'll say, oh hey, I should have done this and it would have worked out perfectly. But you're not constantly you're never that analytical.
Well, especially, auto mechanics is absolutely nothing. We didn't evolve with automobiles, or there's just no way you can't intuitively be a good mechanic. I suppose there might be some element, but without proper knowledge of you could say the anatomy of an automobile and how things work, you can't intuit. You need to gain the knowledge, maintain it, and apply it. And if you're feeling tired or you're just kind of out of it, it would really be the same too. In theory, it's the same for anything that runs against our intuitions. But in physics, it's particularly I don't know if it's pernicious, but it's certainly something that's very common. Now, moving on to our next topic of discussion, fields or quantum fields, which is something that I think, one, there's no way to intuitively grasp these things, and two, I think is a very complicated. Well, it's a confusing topic for people. So let's get into that.
Oh, certainly. So particles and forces are now understood to be the result of fields, and this would be something like an electron. And a field is essentially, you have an electron, right? Well, not really. You don't really have that electron. It's actually it's actually not in one place at one time. This electron, it actually exists across an area. So I'll just explain what a field is. So a field is a mathematical object that takes a value at every point in space and at every moment of time. So quantum fields are fields that carry energy and momentum and obey the rules of quantum mechanics. One consequence of quantum mechanics is that a quantum field carries energy in discrete lumps. We call these lumps particles. Incidentally, this explains why all particles of the same type, example, all electrons, are identical. They are lumps in the same field, example, the electron field. So things like photons, while in physics we can describe them as discrete particles, actually behave as a wave. So they actually get weaker over time. So you'll get less energy density, which means less energy in a given area over time as it permeates outwards through the vacuum. So say you have a point of space and you release X amount of energy. At the next threshold, you move out from that. It expands in every direction and reduces its energy completely. It reduces its energy as it passes out beyond that point in space in a uniform fashion in every direction. So it exists as a field. So it's very strange. There's absolutely no way that we could have known this. Well, I suppose that someone could have thought it up way back when, but that's why this is such a recent thing. Is just recent experiments in quantum physics have just completely changed how we see the world.
Francis, on the point of quantum physics, I think there's a lot of, well, there are a number of things. There are a lot of lay people who invoke quantum physics, not understanding what quantum mechanics, and not understanding really very much of anything about that, to come up with pseudo explanations for phenomena that they either would want to be true or just don't understand. And then this other notion, I've had many discussions with people, and this is a general scientific notion, but this idea that quantum mechanics has quote-unquote replaced Newtonian mechanics, which is incorrect in its formulation. So why don't we, I'd like to tackle those two. Maybe we should start with the latter. Why do people, especially lay people in your estimation, make the claim that quantum mechanics has quote-unquote replaced Newtonian mechanics?
Because it's a more micro level of micro way of looking at things. It's looking at things at a much smaller scale. That's useful, of course, in understanding the fundamentals of physics. So understanding, how light behaves, instead of using more primitive forms of like for instance, light entering a telescope lens. You can describe that with quantum mechanics, or at least I presume you could. But you can also describe it with Newtonian, not Newtonian per se, but with a more primitive form that doesn't look at the basic pieces of matter, but actually just treats it as a macro system instead of a micro system. So Newtonian physics still is useful when we're talking about solving problems that exist on Earth in the macro scale.
Such as trying to figure out how an airplane flies.
Mm-hmm. Quite so. But when we're talking about, for instance, that problem of light reducing itself, or reducing its magnitude, or its intensity rather, and its magnitude, as you move out away from the point of origin, that would be better explained by quantum mechanics, at least on a micro scale.
Right. But it's safe to say that rather than quantum mechanics replacing more traditional mechanical models, it's complementary. And this is, I think it's a kind of trick and artifice used by people to sort of claim that we can. I've seen the way I've seen it employed, whether it's physics or some other field in science, is that that science never really knows, so we don't have any solid state of knowledge about anything. It's just always changing, and one thing replaces the other. I've seen this trick used quite often. The other thing I mention is this. I call it quantum woo-woo. People who know absolutely nothing about quantum mechanics, and I wouldn't say nothing, but little, and you just claiming, for example, that particle displacement can explain all kinds of things, such as quote-unquote free will, souls, that to me doesn't make any sense why they would assume that, although maybe in their own minds it makes sense.
Yeah, I'm not sure about that either, because I had a friend who would do things like this. He would see, like I would point out, something in physics to him, and he would immediately, and he's not so much a friend as he was a childhood acquaintance that I spent a lot of time with. I certainly wouldn't call him a friend, but he would always try to relate things back to some religious aspect. He would always, and I couldn't even follow his thinking. It seemed totally insane to me that he would relate something like electrical energy to the soul, and I can't even begin to tell you anything about their thinking in this regard.
I suspect
it's totally foreign to me.
I suspect it's related to as we progress with our explanatory power of the universe, old concepts and their definitions die out, and people need to latch onto some sort of new way of explaining phenomena that almost certainly don't exist, such as souls or free will or things of this nature, and so they will latch on to, grapple onto anything. And they probably heard some physicists say, quantum mechanics is deeply mysterious, and then they interpret the word mysterious as meaning, almost mystical, and then they can kind of use that as a filter for their own, you could almost say, theology about the way the world works. And that's what my suspicion is, although it doesn't make any sense to me. And I've seen people recently, there was a guy who was talked about soul. I was mentioning souls in relation to energy, and it turned out he didn't even know what energy was. He just talked about energy. So this sort of thing is quite common, and intuitively, that's not even something that's very intuitive. It's just sort of, like I said, latching, grappling onto anything to justify beliefs that don't really have evidence to back them up.
Yeah, and based on things which are totally irrelevant to what they're thinking of. It's absurd to me that someone would use electricity or light, for that matter, to describe something like the soul, which I'm certain doesn't exist. Suppose not certain, but
almost certain,
I don't think so. Yeah.
Or my favorite one is that subatomic, the behavior of subatomic particles creates indeterminacy on a greater scale throughout the universe. This is one I hear all the time.
Yeah, there's actually there's a really good it's really good for lay people, I'd say, to understand this. Is there's if you just go on YouTube and you search quantum mechanics, you can find a really good documentary that goes into this sort of theoretical world where things behave like within within the macro scale of our universe, like the day-to-day life, like you're playing pool, and you hit the cue ball, and instead of going in one direction, it goes in many directions. And that was certainly very visually appealing, and it makes a lot of sense that we wouldn't see it on the macro scale. This sort of what was called quantum spookiness, the electron existing at every point to the same magnitude. You don't see that with cue balls like some people might hope to think.
Yeah, and they then extrapolate things that just are completely unrelated. I've seen this time and again. In fact, I'm pretty sure that someone, upon listening to this in the comment section, will come up with some argument related to quantum mechanics or subatomic particles that is going to be used to justify all kinds of strange notions. But moving on, thermodynamics, really important concept in physics, and one that, again, intuitively, I don't know how humans would ever come up with it or grasp it.
Yeah, it's. I mean, based on our senses, heat, touching something that's really hot, you don't think this thing is just the bits of matter are just vibrating, it's in place. They just have a lot of energy. That's not intuitive at all. I suppose the only way that I could see people being able to, without our modern tools, could understand that, would be something like noticing that as the water, or as this fluid heats up, or this gas rather, as it heats up, it seems to want to, for instance, mercury in a thermometer will rise up the thermometer as it's heated. That's about the only way that I could, and that's just because the matter is bumping into each other and creating a larger gap between the matter, and just pushing each other out in all different directions as it moves, and then the electrons repulse each other, and it moves this way, and then it hits another piece of matter, and or the electrons approach each other, because no pieces of matter are truly touching, really. Although in a black hole you could say they are, because the density is functionally infinite, in that you could not increase it's called a singularity for a reason, because you can't actually increase the density of the object without increasing the area the object inhabits, and that's what black holes are. It's just a bunch of matter so closely packed together that in order to add, let's say a moon enters a black hole, like it's pulled in, the black hole will increase in size. It's not going to stay the same size. But in thermodynamics, there really is no intuitive way, at least by our senses, to know this. I suppose you could say, if you were to drop a large lead weight on the ground and then feel the lead weight and feel the ground, you'd feel that the ground is warmer. And maybe someone sometime could extrapolate that, in fact, the kinetic energy was converted to thermal energy, and that these particles are vibrating in place a little bit more than they were before. That's about the only way that I could see us getting an understanding of that with our senses.
Yeah. And I guess, in general, and before we hit the final point of atomic theory, that so much of our progress seems to have been impossible because, let's be honest, our understanding of mechanics and the physical world really has been the leapfrog for so much of, I mean, everything from airplanes, the internet, to, without that understanding, it seems to me that there are other fields too in terms of medicine, but specifically in terms of physics, we were in a state of technology that really never progressed. It did progress slightly forward, but in terms of the things we have access to, we just could never really innovate to the degree that we can now, just because people relied on the intuitive perception of the world and never went into details. And furthermore, people, even to this day, rely on, well, not intuition in a greater sense, but specifically with regards to physics and the mechanics of the world, their own intuitions as well. Because it's interesting, the way to actually go against your own instincts, you have to actively make use of your prefrontal cortex, which fails sometimes. It's basically a counterweight, and whatever the theory might be, and you're always going to sort of fall back to primarily what you're exposed to as a child, but also what you sort of just perceive to be the case. You shoot a gun, and the bullet comes out, and it just goes in a straight line, of course, in air quotes. That's what it looks like, that kind of thing. So it's incredible to see that once humans deciphered some of these basics, how much more this explosion of progress was even possible, whereas for thousands of years we're pretty much stuck at this, more or less, the same state of affairs. So atomic theory, our final, you could say in some sense that atomic theory, in terms of the danger that was derived from that vis-a-vis atomic weapons, probably the most consequential of all of these ideas. Even a completely smooth-brained person in the public would be, see quote-unquote big explosions and then be worried. So let's talk about atomic theory, and specifically I'm interested, at least, and maybe the audience would be too, in how atomic theory interacted with things like the H-bomb and the A-bomb, etc.
Okay, so let's see. When did atomic theory come into the sort of view of the world? This was in the early 19th century, when discoveries in chemistry showed that matter did indeed behave as if it were made up of atoms. And one very clear way that we knew this was that when you're creating a compound, which is many atoms coming together to form, some new chemical, we noticed that they had fixed quantities, and that you could actually figure out, based on this, how many atoms of or at least what ratio of atoms each element, what each element had, or how many or at least the ratio of elements that come together to form this compound. We could figure that out, and that led to the understanding that it was in fact made up of quote-unquote indivisible atoms. But as far as I know, it actually was thought of in ancient Greece. Of course, the ancient Greeks always you can relate most things back to them. They had some great thinkers. But as we moved forward and we realized that that in fact there was a great deal of energy in some types of matter, specifically uranium, when we figured out that by splitting this you could create massive amounts of energy, that certainly became a problem, especially in modern days, of course. It's totally outside of our instincts to create such a weapon. There's nothing within any sort of modern human that even understands, like from an intuitive level, an explosion. Something like that is just a instinctual absurdity to us. Is there another direction you'd like to go with this? Because I'm kind of
Yeah, I do. Maybe an explanation for the layman. What makes an A-bomb, an atomic weapon, so powerful? What is happening with the atoms?
Okay. So let me think for just a moment. So the uranium. Oh gosh, yeah. So we're talking about nuclear fission. This is either a nuclear reaction or decaying of matter, in which like the uranium-236 or the uranium-235 rather, when we bombard it with a photon, right? It will actually split. So when you hit it with this photon, when you hit it with this photon, it releases a very large amount of energy, and this is because there's a lot of energy holding that thing together, and it will split into what does it split into? Splits into dang it, I'm sorry. Basically, it splits into two different types of matter, and this is because all matter is just a bunch of fundamental particles, and that when you have something that's unstable like uranium, which if I'm not mistaken decays really rather fast because it's got so much energy in it that the rate of decay is actually quite a lot higher. So when you break this piece of matter apart, there's a great deal of energy inside of it that you can then release, which comes in the form of an explosion in some instances, but in others you can actually convert this over to thermal energy, and have nuclear energy like we have now. I'm sorry if that's not a perfect explanation.
No, I think it's a pretty good one. Yeah, I think we've covered many, if not most, of the basis in terms of the intuitive versus how things actually are. I mean, you can always go into a lot more detail, but considering A, that the audience is largely lay, and B, it's exceptionally late where you are, and we had to make a special arrangement for this. I think it would be a good point to wrap up, possibly, unless you want to add anything that you feel is important.
Yeah, no. I think that's a good time to wrap up.
Okay, excellent. Everyone, thanks for tuning in. I hope this was informative. Those of you who are interested in physics might want to make your own observations or knowledgeable, and those of you who aren't, maybe you've learned something. And I think that the takeaway from this, one of the takeaways, is don't necessarily trust your instincts. That is true about women, but it's also true about physics. So everyone take care, and I will check you out later, and thank my guests for joining me. Bye-bye.
Yeah, it was a wonderful time.
Yeah.
Goodbye.
If you liked this video, please like, share, and subscribe. And if you enjoy my content, please consider making a donation or becoming a patron. Thanks for watching.